In this exercise, we are going to use geometry to compute the ratio of the sine of an angle to the angle itself as that angle shrinks to 0. What we will find is that this ratio is actually going to go to 1. Now, if you look at the numerator and denominator of this expression, you'll recognize that both of them go to 0, so this is an indeterminate form. If you've already learned L'Hopital's rule, you might say, hey, why are we doing geometry here? Let's just take the derivative of the top, derivative of the bottom, and show it goes to 1 that way. That's not exactly fair, though, because typically, if you define sine and cosine geometrically, as I usually do, then you need this ratio in order to know that the derivative of sine is cosine. Logically, we want to prove that sine u over u goes to 1 as u goes to 0 in order to be able to know how to differentiate that numerator. So we can't really use L'Hopital's rule here because that would be circular. Speaking of circular, I've drawn here the unit circle, and u is an angle. So let me draw this angle u here. We want to imagine that u is going to 0. So in my picture here, u is pretty substantial, but in this limit, this ray that I've sketched out at angle u is going to drop closer and closer down, down, down to the x-axis. I've situated the geometry here in the first quadrant, but you could also set this up in the fourth quadrant too. All right, I like circles. What I like to also see are triangles. So the most natural step at this point is to take this point on the unit circle, say its coordinates are x, y, and drop an altitude straight down to the x-axis. When we do that, we form a nice right triangle. Given that this coordinate I'm calling x, y, then it makes sense to say the base of this triangle is that value x, the x coordinate, and likewise the height of this triangle is the coordinate y. So there is what I will call the inside right triangle. Let's make a few observations about this triangle. The first one is that the sine of u, the numerator of the limit we're trying to compute, is opposite to hypotenuse. So that's y over 1, or in other words, it's y. So sine of u is y over 1, which of course is y. So this side length here is actually the sine of u itself. And anytime I use y in a computation, I can replace it with sine of u. The second observation I'm going to make is that I also have a circular sector here. It's like the pie slice that you create when you slice into this circle with this ray. The ratio of u, angle u, to the full angle of 2 pi, so part to whole, is the same as the ratio of the part of this area in our pie slice to the full area of the circle. So we have kind of a ratio of circular quantities. Let me write angle for the first ratio versus area for the second ratio, and part to whole, so u versus 2 pi, this ratio is equal to the area of the sector, let me just call that A, it's the area of the sector, to the full area, which is pi times r squared. The radius of this unit circle is 1, so it's really just A over pi. That means the area of the circle, circular sector rather, let me write it over here in the fourth quadrant, is u over 2. So the pi's cancel and we get A equals u over 2. Like that. Okay, I wanted that area because now we're going to compare the area of this inside triangle to the area of this circular sector. Since by construction, no matter what angle I sliced at, as u drops down to 0, we always drew this inside triangle by dropping down inside the disk. The area of this triangle is less than or equal to the area of the circular sector. So I'm going to set up an inequality here. It's going to be the first of 2 inequalities. The area of the inside triangle is less than or equal to the area of the sector. Like that. Okay, Okay, we can compute both of those areas. The first one is 1/2 base times height. So that's 1/2 x times y. The second one is what we called a, so that's u over 2. Okay. See if you can take this, I'm just going to pause for a second, bring in sine of u for y, and see if you can get out of this the ratio of sine u over u. So you should have some kind of bound emerge from this inequality. Okay, here's what I hope you got. We can multiply both sides of the equation by 2. Then y is sine of u. Actually, I'm just going to do it to the right here so I have plenty of room remaining. Y is sine of u. Divide both sides by u, and that will turn into sine u over u on the left. And then I divide by x, and I'm going to have 1 over x on the right. Okay, so that's going to be an upper bound for this ratio sine u over u. We're going to need a lower bound, and here's how we're going to get the lower bound. I'm calling this the inside triangle, so that means there's also going to be an outside triangle. And this one's a little bit harder to visualize. You know, probably as soon as I sketch that point there, you wanted to drop something straight down. Let's make a similar triangle. So I'm going to take this triangle and kind of expand it outwards a little bit so that the base of the triangle is the entire radius 1. So x is less than or equal to the radius. Expand this triangle kind of like this so that the base of the outer triangle is the radius 1. All right, so there we have a sort of tangent down here at the bottom. There we go. Now the comparison is that the area of the sector is less than or equal to the area of the outside triangle, because we start at the radius and we go straight up, whereas the circle goes to the up and to the left. So the second comparison is going to say the area of the sector is the smaller of two areas, because it is less than or equal to the area of this new outside triangle. Like that. Okay, again, we can say what both of these are. So the area of the sector is u over 2. The area of the outside triangle is 1/2 base times height. Here the base is 1 and the height I'm just going to call h. Don't actually know what that is right away, but we can work with it. So 1/2 times 1, that's the new base, times this new height. Okay, again I'd like for you to pause and take a second to see if you can come up with an expression for h in terms of x and y. To do that, you're going to need to use the fact that we have two similar triangles here. So you want to look at the ratio of sides for these similar triangles, see if you can replace h in this inequality with something to do with x and y. And then, if you're already there, go ahead and see if you can get the second bound for sine u over u. This time it should be a lower bound. Okay, here's what we want to do with that height h. Because we have similar triangles, let's create another pair of ratios, kind of like the ratio that we had here. Once again, I'm going to do smaller to larger. So if I look at the bases of these two triangles, x to 1 is going to be one side of my ratio, so smaller to larger, equals smaller to larger, so y to h. Okay, that tells me h is y over x. Like that. Okay, so coming back over here, we have 1/2 y over x, which is actually 1/2 sine u over x. So let me just write sine u. Let me write it correctly. Sine u divided by 2x. Okay. Again, cancel out the 2's, bring the u over, bring the x over, and we get our other bound on sine u over u is going to be x itself is less than or equal to sine u over u. All right. let me write out both of the inequalities now. The smallest is x. So we can say x is less than or equal to our ratio, sine u divided by u, and that's less than or equal to 1 over x. Okay. Let u go to 0. As u goes to 0, the base here is going to slide outwards to 1. So on the left, the lower bound is going to 1. But if x is going to 1, so is 1 over x. So between the two, this ratio sine u over u is being squeezed to 1. So by the squeeze theorem, sine u over u goes to 1 as u goes to 0. Okay, again, this is a foundational limit because we use it to compute the derivative of sine. So it's something that we often introduce at the beginning of a calculus class, and sometimes its meaning is lost on students at that point. One nice thing it says, though, is that the sine of a very small angle is approximately that angle itself. Particularly, sine of 0 is 0. But then if you have something like, what is sine of 0.01? If for some reason in life you ever need to estimate that on the spot, sine of 0.01 is going to be approximately 0.01. Because if sine u over u goes to 1, that means that for very small angles, let me see if I can just write it right here in the middle. If u is approximately 0, then sine of u is approximately u, because the ratio of sine u over u is approximately 1. So again, sine of negative 0.7 is approximately negative 0.7. You can check that. Okay, so I hope you enjoyed this geometric computation here. I really love to work with circles and triangles. Not everybody does, but it is important to see a proper justification of this limit that doesn't rely on the fact that the derivative of sine is cosine. So just how do we compute this limit without knowing anything about derivatives? We do it with geometry.